Hello, everyone. Let me just start this. You just please let me know if you can see the slides. Perfect. Okay. Just wait a few seconds here until people joining. How are you guys doing? Okay. So let me start with stress. Yeah, I know. The midterms, still the midterms. Yeah. It's almost like end of the semester. Yeah. So with weather warming up, I guess there's going to be some hope just having the spring coming in. So I hope everybody's doing fine. Just make sure that you take a good rest and eat well, and things will get better. Okay, guys. So let me just start with the last example that we solved last time. I guess people were kind of doing the calculation themselves, and I think there was like there was some error. And I guess I just found this error because I look at this example. And the only difference here, last time we took this 5 centimeter here, and the 3 centimeter here to be the diameter is actually the radius. So if you actually use 5 centimeter as a radius, that means 10 centimeter diameter. 3 centimeter is radius, that means 6 centimeter diameter. So all the number that we are getting together last time was correct. It's just like I need to make sure that we are using the right radius and diameter given in the problem. So I apologize for that, but all the numbers later on, once we just consider this, it is correct the same way as we did last time. Okay, so today we're going to talk about a very important topic to the fluid flow, in piping, piping system. And last time we spent a couple of lectures talking about the frictional losses. And if you remember, the frictional losses are the losses in a straight pipe that has one single diameter. Okay, so there is no variation in the diameter. There is a straight pipe. It's, there is no bend in this pipe. It's just a straight pipe. And the frictional losses is mainly because of the, viscous forces between the fluid particle and itself, and also the fluid and the pipe wall. And we managed to, do a lot, several exercises just looking into how we calculate the frictional losses for laminar and turbulent flow. So today we're going to continue talking about different type of losses. And I'd like to call these losses as an eddy losses, and these eddy losses is mainly referring to those piping components, because most of the system that we are dealing with in the fluid systems are like, they don't have only one straight pipe, right? They have multiple straight pipe, could be different diameter, and all these pipe are connected by, reducers, right? Are these slides posted? I supposed to, right? I think I did. Because this is same as the last, the continuation of the last slides. Okay, so so those piping components are connected together by reducer or expansion. And also elbows, if the pipe is turning and stuff like that, might have valves and stuff like that, right? So most of the piping system will contain straight pipe as well as small little components that that is creating a certain function on these in these piping system. Okay, so those are the general piping system components. Okay, so when we are talking about, like, you know, the second type of losses, in the textbook you will see it is called the minor losses or local losses, but actually I prefer to call them AD losses or secondary losses. Okay, so I really disagree with you know, referring this as a minor, because sometime you might have so many components, so many small little components, right? For example, in the firefighting system, or like, you know, some of these systems, you know, the total losses of these small little component can be considered to be, like, you know, a significant number, right? So in general, you know, in a big piping system, in a huge, like, you know, this water distribution system, those component losses are smaller, and that's why some people, they consider this as a minor losses. But, you know, the most important definition for these component losses is something called AD losses. Okay, so an AD means when you have a velocity, and this velocity changing magnitude, so the velocity changing its magnitude, for example, like, you know, a pipe that is, you know, changing its diameter, that means the flow rate is the same, so the cross section will be different, so the velocity here and the velocity here are different, right? But, you know, in the same direction kind of flow, you know, we will have something called, like, you know, an AD losses. Or if this velocity changing direction, okay, you know, changing the velocity changing, you might have a pipe which is the same diameter, and now the velocity is going like this. The velocity is now is changing direction. You know, this velocity here, 1, this is velocity here, V1 is equal V2, right? Because this section here and section here are the same diameter, right? So I consider this is the best definition actually to the AD losses. When the velocity changing its direction or its magnitude, you start seeing somewhat we call it eddies, like, you know, turbulence, additional turbulence. This is not the typical turbulence in the straight pipe, but this is an additional turbulence. Okay, let me give you a simple example for that. Let me give you an example for that. Okay, if I have, for example, like a pipe like this, and then I have an expansion. Okay, and this is a center line. What's going to happen here in order to describe the flow is you are considering the flow is moving in a streamline. If you remember what the streamline definition that we discuss in, I think, chapter 4, right? Or sorry, chapter 5. So those streamlines is not a real line. It's just a line that is representing the velocity, the tangent to the velocity vectors, right? So if you are imagining the flow is moving in lines like that, so what will happen in this case, those streamlines, when it's moving in a pipe, it will not change sharply like this, right? You can't have a streamline like this. Why? Because the streamline definition is the velocity at any point is tangent. What do you mean? The velocity has to be at any point here is tangent to the line. You cannot have two tangent at the same time, right? That's why streamline, okay? Streamline is basically something like a smooth line, right? At any point is, you know, only one tangent line. And that's why even the term streamlined kind of shape, it is a very smooth transitional shape, right? So those streams, or this kind of, you know, streamlines, will kind of, you know, move like this, and then we'll try to take the other, you know, diameter, right? So same. Okay, and then you will have more streamline like that. No, right? right? So what will happen in this case? Most of the flow is going like this, right? So most of the flow is going in the main cross section. So if this area 2 and this is area 1, right? We know that this Q here, okay, let me ask you, at point 1 and at point 2, is the flow rate is different? Is Q1 equal or different from Q2? Why? Why is that? Based on any one, guys? Why we say Q is the same as, okay, conservation of flow, conservation of mass, right? Okay, so if for constant density, right? So m dot 1 is equal to m dot 2, and density is the same. That means Q1 is equal Q2, right? Which means that if I have area change, that means if the area change, the velocity will also change, right? But this is basically the main flow, the main, the total flow that is going in the streamline. But of course, this area inside the pipe will not be empty. Like, the flow will go like this. The flow will, try to fill this space. So which means that some of these particles here will start, rotating here, right? Okay. So which means that those turbulence, we call it eddies, okay? Those eddies, right, will be filling these kind of sharp corners and stuff like that, right? So in this case, what we're gonna see here is turbulent eddies, right? And those eddies, in order to keep rotating like that, okay, it just needed energy, okay? And that's why it is taking its energy from the energy of the fluid itself, right? So if you have a fluid that is going in this direction, so this is kind of the eddy that is created because of this sharp, change in the cross section. Some of the other piping could be gradual, piping, expansion. Still, if the gradual of the pipe gradual is not fitting the same smooth kind of, line of the, of the streamline, you still have those kind of eddy. So if you, for example, this is basically what we're talking about in the same direction. How about for changing direction, but this is same velocity? So let's see here. So if we have elbow like this, I'm taking like a very obvious examples here, right? This doesn't have to be like a 90-degree elbow. It could be a different angle type of elbow, but this is, a 90-degree elbow. And the flow is going like this. So let's say here, this one here, and this is 2. So Q1 and Q2 are equal, right? So how about V1 and V2? Diameter here and diameter here are equal. What is the velocity 1 and the velocity 2? What is the relation between V1 and V2? Yeah, but what is the velocity? What is the relation? Are they equal? Are they different? Are they, V2 is greater than V1. Okay, why? Why V2 is greater than V1? Anyone, please help me in this. Gravity. Oh my God, guys, no. Why? What gravity? This is okay. What is that? Okay, what is this? Conservation of mass, right? So conservation of mass has nothing to do with gravity, right? So the mass 1 and the mass 2 are the same. Diameter is the same. That means the velocity are the same. Okay. So if I look at the streamlines here, so the streamline will be, similar to what we discussed, but the velocity here changing its direction from this line here to this line here. Not all the curvature of the pipe will be a streamed line curvature, right? So you might see what will happen here in this case. The flow is going like this and then going like that. Okay. The flow is going like this. It's going like this. Sorry. It's not the best. Okay. So which mean that these are the streamlines. Of course, there's more streamline like that. Which mean that this gap here will have these kind of eddies, okay? And this is basically what will create losses because so basically I will create eddies, and those eddies will take energy from the fluid itself. So those are the eddy losses that we are talking about, right? Once we have a change in the velocity, magnitude, or direction, and sometimes you might have a change in the magnitude and direction at the same time, okay? So like if you have an elbow, but this elbow is going from a small diameter to a big diameter, for example, so still have lots of eddies and so on. So those are the eddy losses, and I hope you guys understand the idea behind the topic of the eddy losses here. And we call it secondary losses here because those are the main losses are friction, but the additional losses are, we call it secondary losses. The magnitude of these ones, secondary or the friction losses or eddy losses, dependent on how many components you have in the system. Sometimes you have piping that has a couple of elbow or one expansion or maybe one valve and stuff like that. You don't have that many components, and at the end those are considered to be smaller number compared to the friction losses, but that's not the case all the time. Okay, so now in order to determine what is these eddy losses are, we develop a certain method, right, to measure the pressure. Like for example here, we measure the pressure here, we measure the pressure here. So we know what is the pressures, right? We know the velocities, right? And also we know maybe the location of these points. And then we apply Bernoulli equation. And now the losses here is only because of eddy. That means we can consider now, the eddy losses using the Bernoulli equation and some measurements. So we determine something called the loss coefficients. Okay. So you will see here, all these loss coefficients is determining the losses because of these eddies divided by half v square. Why half rho v square? If you remember from our chapter 5, when we talk about dimensionless analysis, we all the time like to get those numbers in terms of a non-dimensional units. So we can really evaluate those losses based on some measurements in order to determine these loss coefficients. Okay. What do you mean mass head loss? No, I think it's a meter or something like that. It's not, there's nothing called mass head loss. Okay. a manometer, they call it manometer here, like measuring, using manometers in order to measure the pressures between 1 and 2, right? There's no mass head loss, okay? So we have so many components that we can look at here, and this is our topic for today, is looking at what those type of components. But at the end, these loss coefficient here are determined experimentally the same way as I told you here. Pressure difference, apply Bernoulli equation, find out these losses, and then divided by half rho v squared to convert it into a head, or like a non-dimensional unit. And then you can determine this loss coefficient here as a number that can be tabulated in manufacturers or suppliers of these equipment, right? So every time you go and buy these kind of stuff from the market, those standard component will have coefficients, right? So depend on the shape, depend on the angle, and so on, right? In addition to these, there is so many other things: elbows, tees, fittings, valves, and the valve itself even could be open or closed, because once you have a valve, for example, in this case, you are kind of restricting the flow. That means you are creating more, losses inside these valve. So it depends on if this valve is fully open, you still have a flow inside this valve, versus if the valve is partially closed. Okay, so you see, like, for example, the losses in the valve here, same thing as I mentioned. We look at this, and this is a partially kind of open. Same thing here. So all these losses here is creating these eddies. So you can find out what will be these eddy losses by calibration in the lab, or the people are manufacturing this valve. They will provide you with an information about what will be the loss coefficient of these valve. Of course, it depends on the type of valve, because we have many kind of flow valves available in the market. The first one here is a gate valve. This one here is a globe valve, the angle valve here, swing valve, disc valve, so many kind of valve. And it's just not limited to these pictures here, but there is so many kind of valve. Once the flow itself changing directions, and even internally the velocity changing here because of the areas changing inside the valve, you will start having eddies, and those eddies are taking from the energy of the fluid, which means reducing the head of energy of this system, or the energy, the total energy of the system. Okay. You will see here, for example, this is a typical kind of engineered product, right? So this is a gate valve, and this gate valve here is given at a different angle. So when you are opening or closing this valve, you will see here the valve opening here. If it's 20 degrees, 30 degrees, 40, 50, you will see this K, which is the loss coefficient inside this valve, will take different value here. Okay. So, and again, different diameter also of this valve might have a different value for this K, the coefficient of losses inside this valve. Okay. So another thing here, for typical example of a chart that is given. So loss coefficient valve, this is a chart here, right? This chart here basically is giving different type of valve, right? Depend on the fractional opening. Is it 25% open, 30% open, 40? If it's fully open, it's going to be, like that, right? So some of the other valve here, for example, you'll see that the disc valve here will have almost a zero loss coefficient. But for a globe valve, because the structure of the globe valve itself, you still have, even for a fully developed, you have a value of loss coefficients. Okay. So those are not the only charts. Those are not only numbers, right? Those are just a sample of what is available in the fields and in the commercial fields. So you just need to find out what is the right chart or tables, right, that you can use these loss coefficients here in order to determine the losses, the eddy losses in the system. Okay. Same thing for elbow. If this elbow is long radius, okay, or if this elbow is a short radius, like, you know, something like that, right? So it all depends on what kind of curvature of this elbow, right? You see here, like, you know, this is R over D. So this is the curvature radius divided by the diameter of, the diameter of the pipe, and depend on, like, you know, the ratio. You will see, for example, here, different kind of elbow. This is a 45-degree elbow. This is 90-degree elbow. This is a 180-degree elbow, something like this, right? So, so this is basically giving you values for K at different R over D, okay? How the velocity equal if the RAD loss? So losses in the energy doesn't mean losses in the velocity, right? Velocity is always defined by the conservation of mass. You have a flow, you have a mass. This mass is going from one point to another point, right? There is no leak. That means the flow rate here and the flow rate there is the same. Area changing, the velocity change. Okay, you might have even losses, but the velocity increase because the area is decreased, right? So we don't really consider velocity change here because of the losses. Okay, but what we are seeing in terms of losses, we're gonna see here, like, you know, in a few seconds here when we start talking about, like, you know, the total losses in the piping, right? What is the losses in the system is creating? You know, what is the main parameter that you will see decrease because of the losses? We'll get to this in few seconds. Okay, and I will respond to how this you know, how is the losses, the eddy losses, but again, how all the losses is affecting the flow, okay, in the piping. So same thing here, you know, entrance losses. What do you mean entrance losses? Like, for example, a tank like that, and then you are kind of, you know, you're having the flow is coming inside this tank. We call this is an entrance losses. Okay, some of these, you know, tank and then a pipe, right? If you have a sharp entrance like this in the pipe, or if you have, like, you know, a pipe that is curved like that. Okay, so, or like, you know, flatted kind of, you know, like this here, right? Again, different charts. Okay, and you will see here, for example, the chart will giving you a certain dimensions. You just follow what is given in the chart, right? And try to find out your loss coefficients. It's a very straightforward thing once you look at the chart, just to find out your K, right? Again, I'm just giving an example because you might see a completely different, you know, chart in the market, depend on the manufacturer itself. Okay, you just try to find out your K from the chart given the condition presented in this chart, right? So what is the diameter, for example, here? What is, for example, here? What is, like, you know, this L here over this D, right? And find out K at a different theta, in a different angle here, right? So thousands and thousands of charts is talking about how to determine the loss coefficients, right? But at the end, it is a very simple problem. Once you find out this K, right, the loss is basically, again, this is, you know, this is a sudden contraction, this is a sudden expansion, right? So this is a line for sudden expansion, this is a line for sudden contraction, and this is D over D. So, for example, here, the small diameter over the big diameter, find out this value, and then, you know, you go and find out, for example, here, you go and find out your K, okay? Okay, so at the end, what you're gonna find, again, this is a gradual, you know, a gradual change pipe. You will see again, you know, for different D over D, like this diameter here over the diameter, several lines, okay? And based on the angle, right, this angle theta, you know, once you have this angle and then you have this L D over D, you can find out your K, right? At the end, you can basically determine this H loss as KV square over 2G, right? Once you find this K, you can find out H loss, okay? And the velocity here is dependent on the equation that we're gonna see now in another table. So sometimes you get it as a chart, but also sometimes you get it as tables like this, okay? For example, it's giving you different component here, and was giving you here either screwed component, like, you know, the component are screwed together, or these components are flanged, right? So sometimes you have these piping here that is, you know, flanges and connecting, like, you know, right? And then you have flanges like this, or you have, like, you know, these screwed, you know, component, for example, like this, right? So it depends on this, and also depend on the diameter of the pipe that you're basically getting, and the type of component. You can get whatever, like, you know, your K that you are looking for, 1 inch, 2 inch, half inch, 4 inch, and so on, okay? Yeah, H loss. H, not E, it's HL. Okay. So typical resistance coefficients are, like, you know, this is what the losses, you know, for different components. You will see here, for example, you know, from tank to pipe, okay, the velocity is given 0.5 v squared over 2g, right? This is another table that is available also in many, like, handbook for fluid flow in the system, which means that the K for this case here is 0.5, right? You know, some rounded pipe of 0.05. So if this is kind of a rounded, right, or projecting conditions, that mean, you know, it's kind of something like, you know, protruded inside the tank. But again, this is not the limitation of these chart or tables. You might see a, you know, other type of chart, but at the end, what we are looking for here is a loss coefficient, okay? And this loss coefficient is a unique for every single component, and also unique for the manufacturers. Like, you know, different manufacturers will design those components differently, and you have to test it in the lab, like the same way as I mentioned, and determine what will be the K losses, or the loss coefficients, which is in order to determine the head losses. What do you mean head losses? You remember when we talk about hydraulic gradient and the Bernoulli equation, all the time we are creating the losses in terms of heads, right? In terms of meter, right? Because we are getting a non-dimensional, number of these loss coefficients. And then if you multiply these by v squared over 2g, you're basically getting the value of losses in terms of head as meter, or as lengths, right? Okay, so let's look at, you know, an example for this so you can understand what we are talking about here. Okay, but just before the example, just to answer a couple of the questions here. Okay, if I have a vault, like, imagine if I have a system like that. Okay, imagine I have a pipe like this, and then you have a 45-degree elbow, and then, like, you know, another 45-degree elbow. I have a valve here, and then I have a pipe like this, and then here. Okay. And imagine all this are on the table, like, you know, all this on the horizontal plane, right? There is no elevation here. Okay, you can imagine that. So those are on your desk, right? Laid out like this. So that means every point here has the same Z. Okay, so this is horizontal. Okay, now the flow is going like this, right? So between 1 and 2 and 3, 4, 5, 6, 7, and so on, right? So every time you are going through a piping system, you are losing energy. You agree with me? So every time you're going, you're gonna have friction, right? So in a straight pipe between 1 and 2, what do you have? What type of losses you have? Guys, you start, okay, so you stop at trying to distract me from the main ideas. Okay, so this is not 2, this could be whatever, okay? From 1 and 2 here, like 1 and 2, what is the losses here? What is the type of losses? Friction, yes, okay. Do I have eddy losses between 1 and 2? Yeah, I agree with you. Like I was confusing and giving you 2.2. Yes, sorry about that. From 1 to 2 is basically, it's like friction losses. Okay. So between 2 and 3, just before the contraction and just after the the contraction, what type of losses do you have? Eddies, right? And then from 3 to 4, friction, right? And then 4 to 5, right? So it looks like as the flow is going, is losing energy because of friction, and then as the piping changing, you have eddies and then friction, right? If I go to point, X here, so between 1 and X, what will be the total losses? Is it some of these or like all of these? So it is basically the summation of all the losses, right? So what we are saying here is basically like, we have a piping system that is connected in series, right? So the end of the first component is connecting the first of the second component. The end of the second component is connected to the third one, and so on, right? As if you are connecting the system into series, right? So now when we are having an energy, right? If we apply Bernoulli equation between 1 and 2, or sorry, 1 and X, right? B1 over gamma plus Z1 plus V1 square over 2G equal B2 over gamma plus Z2 plus, sorry, X, yeah. Sorry, guys. X Vx square over 2G plus H loss between 1 and X, okay? The velocity, the potential are, the same, right? Okay. The velocity change could be the same. Like, this could be like, small, almost the same diameter or even small number, right? So the variation of the velocity is not that much, right? So even this one and this one here could be different, but slightly different, okay? So now these H losses here is mainly what? Is B1, V1, right? Which means that the losses in the piping is mainly creating pressure drop, okay? So this is something keep in mind when you are dealing with any fluid in systems like this, okay? So in a piping system like this, you will see a pressure change because of the losses, okay? So if you are measuring the pressure here, and if you are measuring the pressure here, so this is Bx, and this is B1, you will see a reduction of the pressure. So the pressure will drop as you are losing energy inside the system, okay? So the velocity is not changing because of the losses. So this is just to answer the question that I got just a few minutes ago. Okay, so let's look at this problem here so you can understand what we're talking about here. So we have two tanks here, and the dimension here are given in feet, right? And the density also is given in slugs per feet cube, so in British system. And the viscosity here, sorry, this is not V, it's just like a viscosity here, okay? kinematic viscosity, feet square per second, is pumped between the two reservoirs at 0.2 feet cube per second. So this Q, or the flow rates, right, between these two tanks is 0.2 feet cube per second. Okay. The diameter of the piping, it's 2 inch, right? There's no change in the diameter all over the system. So the diameter is 2 inch. And the pipe had several minor losses. Okay, and this is what is written in the textbook. So several eddy losses or component here, or minor losses, as you can see. As shown in this figure, the roughness ratio is epsilon over D is given as 0.001. Is trying to determine, the power of the pump. Okay, let me ask you first one question. If I want to remove the pump, okay, it looks like the pump, the flow here is going from this tank to this tank. You see that the arrow is going like this. Now, if you want to remove the pump, what's going to happen? If I would remove the pump, just replace the pump by a strip pipe, just like. Where is the flow will go? What will be the direction of the flow? Why, Ethan, the flow will reverse? What is it? Okay, and the elevation is what? What is the elevation is representing in this system? The elevation of the tank is representing what? What did we call the elevation of the, potential, but another better name for that. The elevation of the tank is considered what? No. Just the elevation of the tank is considered to be, yes, I know it is potential, I know it's head and stuff like that. But what is the total, what is this elevation is representing? Is representing energy, right? You remember when we talk about the total energy line, we said the elevation of the tank is energy because the velocity inside the tank is 0. So V square over 2G is 0. The pressure at any point inside the tank depends on what is the head above this point. So B rho G H, and then you divide it by rho G, or gamma H divided by gamma. This would be the head of this tank, and then the location will be Z. So the total of this will be the elevation of the tank. So the tank is representing an energy at this point here, right? So if this is a point A, so this elevation here is representing the energy at point A. This elevation of the tank is representing the energy at point B. Okay, which means that if this elevation is 20 here and 120 here, if we are removing the pump, the flow will go from the high energy to the low energy, right? So this is the idea of the fluid flow. So we are using the pump in order to drive the flow in the opposite direction. So that's why we needed an energy N, right? So in addition to this energy, I need to add energy into the system, which we call it, like, for example, if the energy all are represented by head, so we're gonna add H pump here, head of the pump added to the system, added to the energy at point A in order to drive the flow from A to B. Okay, so now if I look, for example, here at the solution, so I know that BA over gamma plus ZA plus VA square over 2G. This is all the heads, right? Okay, plus head of the pump. because you are adding energy to the first point of the energy, equal to BB over gamma plus ZB plus VB square over 2G. This is the energy at the final point. And the difference here is basically the losses, right? Plus H loss between A to B. Okay. So now this total energy here is the tank level. This total energy here is a tank level. So I can say this is total here is 20 and this is 120. Okay. Which means that H pump here is 120 minus 20 plus H loss between A and B. So this is 100 plus H loss A to B. Okay. Now losses between A and B, this all piping are kind of, connected. So we have first, you have sharp entrance to the pipe, and then a straight pipe, and then, a globe valve, and then, the pump here is, it's you can consider it as a component, but there's nothing here mentioned about this pump, any components, only given this kind of, diameter and all this elbow, 20-inch bend radius, 90-degree elbow, globe valve. It's telling you all this piping has, a length of, the length here is given as what? 400 feet. Okay. So the total length of the pipe, 400 feet. Okay. So consider all the lot, because they are all at the same diameter, right? So those small little pipes, all 2 inches. This pipe 2 inches, this pipe is 2 inches, this pipe 2 inches, this pipe 2 inches, right? So the summation of all these losses in a straight pipe, we call it the friction losses, right? So in this case, so I have 100 plus friction loss, right? Which is F L over D V square over 2G plus summation of K V square over 2G. What does the summation mean here? All the AD losses in the system, and all are added in the system, because the total energy losses is all the friction in a 400 feet pipe plus all the losses because of the component on this pipe. Okay. So what we need to do here in this case, so we just start the same way as we did in the previous lectures. We get the velocity, we get the Reynolds number, we get the friction factor, and just, do all these kind of things. So we have Q, right, is area times velocity, and the pipe has a 2-inch diameter. So this Q here is 0.2 feet cube per second. So let me put the area here is in feet square. So this here is pi over 4. The diameter here is 2 inch. In order to convert it to feet, so it's 12. It's 2 over 12. Right? It's 2 over 12, right? In terms of feet, and then square times v is 0.2. So which means that the velocity here 9.17 feet per second. Just to confirm, BA equal BB? No. No. So BA, how BA and BB are the same? How is that? It's not, there's no relation here. Okay, let's go back one step. So what I did talk about for some time is the energy of the tank, the level of the tank is the energy. So if you're taking any point at any, inside the tank, the energy at the end is that. Okay. You can take this point here. You want to take this point 1 and this point 2, right? In this case, the pressure is 0, right? If you take this 0.1 and this 0.2, right? You can do the same. You can do this, right? That's fine, because 1 point inside the tank, but it happened to be at the surface of the tank, right? Now the pressure is 0 and B2 also 0. Now the Z is 20 and the Z here is 120, and then the velocity is 0 here and 0 there, right? I know it's like, I'm trying to make you understand the, like, you know, the core, like, you know, of this idea that any point inside the tank will have a total energy that is the level of the tank, right? Doesn't matter where these points are, okay? One will be like at the top of the tank, so all the energy are Z, right? I'm not sure, like, do you guys understand what I'm saying? Because I can't follow the comment that you are making on your chat. I don't know if this is in the direction of your understanding or not. Is that, are you following? Are you following or no? Yeah, okay. So it means that if you select a different point inside the tank, at the end is the total energy will be 20. So depend on where you select these points, okay? So I want you to think about this, because sometimes, imagine, let me give you an example. Imagine I give you a tank that is closed, okay, and it has pressurized air at the top of the tank. Okay, now we cannot really do this 0.1 and 0.2 at the level of the tank, and you are seeing this energy. You have to really consider also the pressure at the top, right? So in general, level of the tank that is open to atmosphere representing the energy of this tank. Okay, let me get back to what I was trying to explain. So I have the velocity here, which is 9.17, and then I can find out Reynolds number by, so Reynolds number here is VD over nu. The velocity here is 9.17. The diameter is 2 inch, but it has to be in feet, so I can make sure that everything is the same unit. The viscosity, the kinematic viscosity is given as, you know, this value here in feet square per second. So 0.000011. So this value here is 139,000, right? So, and we have epsilon over D that is given also. First of all, this is a turbulent flow, right? So this real number here is very high. So I can get this, you know, from the Moody chart. I have epsilon over D and I have Reynolds number. I can get, you know, the friction factor. So the friction factor here is 0.022, right? So the friction loss is straightforward, right? What is new here is we know that in order to go from point 1 to point 2, or from point A to B to point B, I will have to go through, like, you know, multiple, you know, components, right? That is creating all these eddy losses, and that summation of these losses will be added together, right? So in this case, I need to find out the K first for the sharp entrance, right? So you will see here. So this sharp entrance here first, the first thing, and then globe valve, right? And then elbow here, long radius elbow, because this is 12, you know, bend radius, short radius elbow, half open gate valve, and then sharp exits. Okay, so we'll just go into one by one. So first, you know, pipe to the tank. So this is, you know, an entrance, sharp entrance, right? And if you can see here, this is a sharp entrance, and this point here, because L over D, if this is sharp, see here, this is sharp entrance, right? So the radius over D is 0, right? So these are the point here. So K here is 0.5. Okay. So these are the first coefficient of, you know, eddy losses, right? The second one is open globe valve, right? So open globe valve installed in a 2-inch pipe diameter, right? So globe valve, this is fully open. Okay, we have two options here, flanged and screwed. Okay, it doesn't look like there is a flange here, right? So, and again, you know, more description you should have in the problem in order to make sure that you are not confused. But it looks like there is no flanges in this valve here. So open globe valve, 2-inch diameter. So this is a 2-inch diameter. So it is the K of this valve here is 6.9. Okay. And then you go again to the long radius elbow. The long radius elbow here, the radius given as 12-inch, right? Which means that R over D is 12-inch and the diameter is 2-inch. That means this is 6. That means it's somewhere here. And this is a 90-degree elbow, right? You see here, this is a 90-degree elbow, right? So you can look at this. So this is a 90-degree elbow. And at 6, so you can get your K. So K of the bend here is 0.25. Okay. And then you go again to 90-degree elbow. So 90-degree elbow, you'll see here 90-degree elbow, but this is not a long radius elbow, right? So typical 90-degree elbow, and this is a regular 90-degree elbow installed in a 2-inch pipe. So the K of bend 2 is 0.95, okay? It's going to be like a systematic approach of solving this type of problem. And most of the design problem is something like that, right? So you will find out all the component, find out all the K for these components, and make sure that, you know, you are using the summation of this K if you are connecting this piping in series, right? And then the next one is, so after this elbow, half open gate valve. Okay, so half open gate valve. So this is fully open gate valve, right? So half open gate valve, we have to find a chart like this. So the chart that is giving you, you know, the fractional opening. Fractional opening here, 50%. Half open, right? And this is a globe valve, right? This is a globe valve. It's actually this one here, which is this here. Right? So I have a number here that is 3.8. Not sure if this is very accurate, but let's say, for example, K of this valve here is 3, for example. Okay. And then sharp exit. So because that's the last, you see, this is the last one. So pipe to a tank. So the tank diameter is infinity, like it's a big diameter, right? So the diameter over D is like 0, right? D small of the pipe divided by the diameter of the tank is 0. So you see here, sharp, you know, exit, right? Imagine if this is a tank, that means D is big. So D over D is almost 0, right? And you'll see here, the value here is, you know, for this sudden expansion here, K of the exits is 1. Okay. Blue line, isn't it other blue line? What blue line? What is a blue line? Yeah, I don't know. I can't follow those type of questions. So the Sharpe entrance in diameter infinity large. Yeah, K for like a pipe to you see, remember, like, you know, when we said, for example, there are some other, you know, tables given in many charts, like for example here, you see here, tank to a pipe or pipe to a tank, right? So this is basically the opposite here. So pipe to a tank, right? You see here K is 1, right? So this is a very common number that you will find in many other charts. Or if we are using this chart here for Sharpe entrance, this is an expansion, right? So we have an expansion. So this is an expansion. So this is a line we're talking about. But now this is a tank. That means D over D is 0. So we'll go here to the expansion, and then K will be 1. Again, it's all related to the color, guys. You see it on your screen, right? So it's, unfortunately, like, you know, the textbook is using. Okay, okay, so I hope you guys get to the core point of the understanding. Like, I don't think we're gonna stop at these little stuff. So I think the globe valve here is this. Is it the globe valve at the top one or the bottom one? Yeah. Yeah, it should be clear in an exam, right? Or it should be a better clear here. I can't see, to be honest, the difference between the two blue line. But I remember this is basically your line that we're talking about here, right? That's not really something we're going to stop us from carrying out on the problem, right? And if you make a mistake based on you didn't see the color, for example, in the charts, that's forgiven, because I don't do. I make the same mistakes, right? But what I'm saying here is, like, look at the most important idea that we're, you know, kind of discussing here. Okay, so those component that is added in the system will, for each component, you will have some access to information about something called loss coefficients. Okay, and these loss coefficients is basically, like, you know, depend on the manufacturer, depend on the information provided to you. Is it table? Is it chart? Right? So it is a very straightforward, to be honest, like, you know, you're getting those numbers from those charts, right? You just need to make sure that you are reading the question correctly, right? Is that a globe valve or a gate valve or something like that, right? Is that a Sharpe entrance? Is it like a gradual expansion, or like those kind of things? Once you identify these values, you will basically find out the K for each of these components, right? And the idea at the end here is basically you in order to calculate these losses is, you know, for a pipe component in series like this. So going back to the equation that we put together, right? Like this, right? So this is equation 1, right? So H pump will be function of all this. We get F, right? We have the velocity because, right? We just need to add these values here for K, right? So let's go back again and put these number. So we have H pump. H pump is, I think somebody opened the speaker, so if you please don't mind, mute yourself. So I have this, and then loss fraction is F, right? L is 400 feet over D, which is 2 over 12 inches. So 2 inches over 12. So you can convert it to feet. So just make sure that everything we have here in feet. And the velocity here is 9.17 square divided by 2. G here is in feet per second square, which is, 32.2. So all these are the friction losses, right? Plus summation of of K, right? V square over 2G. V here is 9.17, G here 32.2. And if you added all the K, right? So you can add all these K that you divide, like you got, right? Like for example, here for this valve that you guys are concerned about, which line here, I have K here is 3.8, which is strange from this equation. Okay, so please forgive me if there is a small little deviation from the the number here, but again, we're just focusing on the most important piece of information we need to discuss today. So this K, summation of K here is 13.4. Okay, so in this case, we can calculate H pump, and H pump here is 185 feet. Okay, so now in order to drive the flow at 0.2 feet cube per second in this system, I needed head from the pump, a head increase from the pump, a pump that is providing, and the head of the pump is the energy, right? So basically, this is what the energy for the Bernoulli equation, each term representing energy, but in terms of feet. You need to find out, for example, this energy or the power. What is the difference between power and heads? What is the power? Pump power. I know H pump, right? If I multiply this pump by gamma, this will give me what? What is gamma H pump? If I multiply the head by gamma, what is that? Pressure, right? And if I multiply this by Q, remember, pressure times Q is power, right? So the pressure times the flow rate is power. So the flow rate of the pump, the pressure of the pump, this will give you the pump power, right? So I know this is gamma here is rho G, right? Rho G here is 1.9. I think it's 1.94. This is what is given in slug per feet cube, right? Is that correct? Yeah, gamma here is 1.94, right? Sorry, density is 1.94. So gamma will be rho G. So rho times G 32.2. This will give you, rho G, right? So times 185. This will give you pressure times 0.2 feet cube per second. This is the flow rate. So this will give you about 2,300 feet bounds per second. Okay. In order to convert this, if you want to convert this in, because we're using a British system here, if you divide this by 550, you convert this value here. So this will be 2300,550. You convert this into horsepower. So 41.2 horsepower. Okay, I like the distraction mechanism. Okay, midterm. Okay, midterm feedback. I don't know. Yeah, sure. We should be able to see that. I don't know why you guys still asking about that. I publish the feedback, so I don't know how many people are still not seeing this feedback. So everybody can't. Okay, I will check with the course link, because I tried to, many things, and it should be available to the students. Even when I register as a student, I can see the feedback. So when you look at the grades, it might be a question mark that is showing on the grades. If you click on it, you will see your feedback. So I will, again, I'll check. Now I'm out of the focus that I had. Okay, so I don't know, I think we have 5 minutes already. So we'll stop here and then we'll get to the rest of this lecture next time. Okay, can we please see it? Yes, I have no problem. You see it, Zaina. Like, you know, I didn't say you cannot see it. I will try to see how can I get you access to see it. I set up like the quiz so you can see the feedback. So let me check this technical thing. Okay. Good. Anything else? Anything else, guys? Any questions? Any questions? Okay. No problem. Okay. Take care. So we're gonna stop recording here, and for the people who wanna stay for question, I know you guys know that I have my office hour after the lecture, so I can stay in the same link and just waiting for your questions.